Okay, let's get started. So today we're going to be covering permutations. Now, permutations are one of the things that once we cover it in this section, we're never going to come across it again in this class with how we're going through the book. But the reason I include it anyways is to try and force you to get very comfortable with function composition. So we're going to go through a bunch of stuff here. It's going to get kind of complex for you. But the homework problems are going to be really easy. So you're not going to have much of a problem with the homework problems, I don't think. This is probably the difficulty of the section compared to the homework I give you. There's the biggest difference. The homework is very easy compared to the material that we cover. The purpose here isn't necessarily trying to help you understand permutations. It's giving you a field of math where we use function composition over and over and over and over again to try and get you comfortable with function composition. So that's what I'm really trying to do here, and permutations is just my way of doing that. So it's something that's going to come up, we're going to do it here, and then permutations aren't going to come up again in the class. So what is a permutation? Let A be a set, then a permutation on A is a bijection from A to A. Now, what's a bijection?
It's a set that's both onto and one-to-one.
A function that's both one-to and or both onto and one-to-one, right? And so if it's a function, so if a permutation, if it's a bijection from A to A, what does that mean? That means it's a function that maps everything in A to one and only one thing in A. So everything gets mapped to something, nothing gets left out. Make sense?
Yeah.
So let's look at an example real quick. Let A be the set 1, 2, 3, 4, 5, and let pi, typically we use Greek letters to signify permutations. So I'm going to be using pi a lot, sigma a lot, iota for the identity, and then there's another one, but we'll see it when we come across. Okay, so let A be the set of numbers 1, 2, 3, 4, 5, and let pi be a function from A to A by pi is equal to this function. Maps 1 to 2, 2 to 4, 3 to 1, 4 to 3, 5 to 5. Is this function 1 to 1?
Yes.
Yes. I never have two things mapping to 2. I never have two things mapping to 4. I never have two things mapping to 1 or 3 or 5. Only one thing. So for every output, there's only one input, is one way you can think about that, right? Is it on 2?
Yeah.
What does it mean to be on 2?
For every input, there's only one output.
No, that's a function.
It uses all of your right-hand element.
Oh yeah.
Yeah.
That's right.
What's the range or the image of this function? 2, 4, 1, 3, 5. Is that all of A?
Mm-hmm.
Yes. So it's on 2. So it's a 1-to-1 and an onto function. It's a bijection. It's a bijection from A to A. In other words, it pairs everything in A with something and only one thing in A. So the way we say that is 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. Now notice, the range of this thing is 2, 4, 1, 3, 5, where our inputs were 1, 2, 3, 4, 5. So the output, if you put the output in a list, is just a reordering of the numbers 1, 2, 3, 4, 5.
Yeah.
And that's what permutations do. They say, hey, put 2 first, then 4 second, then 1 third, then 3 fourth, then 5 fifth. 2, 4, 1, 3, 5. It's just a way of ordering those numbers. That's why we call it a permutation. With me so far? Okay. So, if we're given a set A equal to 1, 2, 3, 4, 5, 6, all the way up to n, from here on out for this lecture, we're going to use S sub n to represent the set of all permutations on A. Question. How many permutations could I create on this set? 1, 2, 3, 4, 5.
5 factorial.
5 factorial. How did she get that?
How did she get that?
So let's look at just a blank permutation. So I need to map 1 to something, 2 to something, 3 to something, 4 to something, 5 to something. How many options do I have for what I can map 1 with?
5.
I have 5 options. How many options do I have for what I can map 2 with?
4.
4.
Why don't I have 5?
Because you already used 1.
Because I can't repeat. If I repeat, it's no longer 1 to 1. So then I only have 4 options for this, and 3 options for this, and 2 options for this, and 1 option for this. So there's 5 times 4 times 3 times 2 times 1, or 5 factorial ways that we can finish this off. Right? So there's 5 factorial permutations on A. So given A is equal to 1, 2, 3, 4, 5 all the way up to n, and Sn is a set of all permutations on A, how many elements are in Sn?
And factorial.
N factorial. Sn is a set of all permutations. It's the set of all the functions. It's a set of permutations. How many possible permutations are there if A has n elements? There's n factorial possible permutations. So Sn has n factorial elements. Does that make sense? Don't lose track of the fact that Sn is a set of functions. It's a set of permutations. What are the elements of Sn? Any way that we can finish this out, whatever pi that gives us is an element in there. Does that make sense?
Okay.
Okay. And then the identity function. Notice that the identity function is a permutation, right? One permutation I could have created is I could have mapped 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, right? So identity function, that's permutation. It's 1 to 1, it's on 2. So in general, we use iota, the Greek letter iota. It's like an I without a dot at the top. Iota to signify the identity permutation. Make sense? So if I tell you that iota is in Sn, what does that mean? That means iota is equal to 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, all the way up to nn. Make sense? Iota is in Sn. What is Sn? It's a set of all possible permutations that you can make on this set. What's the identity function on this set? It's the function that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, all the way up to n to n. Does that make sense? Okay. We got that. Okay, so properties of Sn. We've already talked about one of them. How many elements are in Sn? N factorial. Let's look at another property. For any 2 permutations in Sn, their composition is also in Sn. Okay, how do we know that one? Maybe we'll come back and talk about property 2. Property 3, what does property 3 say? Given 3 permutations, then how you compose them together is associative. We already proved function composition is associative, right? So we already know this property. We already know this property. We'll go back to 2. Let's look at this property. This property says for any permutation, the identity composed with that permutation is equal to that permutation composed with the identity is just equal to that permutation. We already proved that for identity functions, right?
Yeah.
You remember that? So we've already got that one. What about this one? For any permutation S of n, its inverse is a permutation. How do we know that?
Is it because of bijection? The inverse of a bijection is still a function.
The inverse of a bijection is a bijection. Not only is it a function, it's a bijection. Right?
Yeah.
No? If a function is 1 to 1 and onto, think about its inverse. Is its inverse still 1 to 1?
Yeah.
Yeah. Is its inverse still onto? Yes. It better be. Okay, so for every permutation, its inverse is a permutation, and the second part you already proved, right? A function composed with its inverse is equal to its inverse composed with itself is equal to the identity function.
Yeah.
So we've already got that one. Now let's go back to number 2. How do we know number 2? How do we know that the composition of two functions is in there? Well, think about it this way. Is the composition of two functions, of two bijections, a bijection? Yeah. How can we check that? First off, a function composed with a function is a function, right?
Yeah.
Yeah. These are both bijections, so both their inverses are functions, right?
Okay.
So the inverse composed with the inverse is also a function. So the composition is 1 to 1, and it has to be on 2. Because otherwise the inverse can't be 1 to 1, because it wouldn't be a function.
Okay.
Does that make sense? If you have a set A and a set A again, and pi maps everything in A to A, then pi inverse has to map everything in A back to A. If we know that pi is 1 to 1, and it maps everything in A to A, we already know it's on 2. Okay, so we've got this property for permutation. So the permutations have some nice properties. And those of you who did logic might notice that that's some of the properties that we kind of assumed when we were doing some basic proofs. You might remember that we started out with one system where it had an operation with an identity element, and also the operation was associative, and that's all we knew about it, and we proved stuff with just knowing that. Turns out everything you proved is true when we're talking about composition on permutations. This is just a special case of what we did in that logic class. Anyways, moving on. Notation. We definitely don't want to be listing our permutations out like this. That's a lot of work. We hate doing that, right? So we're going to try to come up with shorter ways to write permutations. So let pi be, oh, I erased what we had here. Shoot, I didn't realize I referenced it again. So let's see, what was it? It was
2, 4, 1, 3, 5.
2, 4, 1, 3, 5. Nice. Okay, so we got pi as this function, and now I'm going to represent it this way. So here's another way that we might represent a permutation. And here's how we think about it. Here's our domain, here's our range, and we line them up so that 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. So this is another way of writing the same permutation. We can write it this way. Make sense?
Okay.
Now when we write it this way, obviously the top row is always going to be just 1, 2, 3, 4, 5. So why waste time writing the top row? Let's just write the bottom row. Right? So this is what 1 went to, this is what 2 went to, this is what 3 went to, this is what 4 went to, this is what 5 went to. Another way that we can write this is cyclic notation. So before we look at the actual notation, let's draw a graph of what this thing might look like. We know 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. So let's draw that. So 1, what does 1 go to? 1 goes to 2. What does 2 go to? 2 goes to 4. What does 4 go to? 4 goes to 3. What does 3 go to? 3 goes to 1. And then 5 just goes to 5. You see how we can create a graph from this permutation? Huh?
That's cool.
It is cool. Anyone have any questions about how I went from this permutation to this graph of the permutation? Okay, so then we also have what's called cyclic notation. And the reason we call it cyclic notation is because it captures the cycles if we were to graph this thing. So how do you read cyclic notation? We say 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes back to 1, and then 5 goes to 5. And you keep doing that for every cycle you have. If I had 7 cycles in this function, I would have 7 sets of parentheses representing each of those cycles, where the left-hand element always goes to the right-hand element. Not the left. An element always goes to whatever's to the right of it, unless it's at the end of a cycle and you come back around. Make sense?
Yeah.
Okay, that's called cyclic notation. And we're going to use it all the time. It's a very convenient way to write functions, or permutations, and that's the one we're going to use the most, not these other ways. So let's get comfortable writing cyclic notation. So I've got this function pi. 1 goes to 2, 2 goes to 7, 3 goes to 5, etc. You understand what this function is? and it's a permutation in S9. So now I want you to tell me how to represent this in cyclic notation.
So 1 goes to 2.
1 goes to 2. What does 2 go
2
to?
goes to 7.
What does 7 go
7
to?
Back to
goes to
1.
1.
Okay, so we're done with our cycle.
Yeah.
Well, no, you have another set of parentheses.
Right, but we're done with this cycle.
Yeah.
So 1 goes to 2, goes to 7, goes to 1, goes to 2, goes to 7, that's a cycle. So now, as a matter of convention, we start the next cycle with the next smallest number we haven't used yet.
So 3.
You don't have to. There's a bunch of different ways you can write these. It's just convention.
So 3 goes
So
to
3
5.
and 5.
5 goes to
And
5
then
goes to 3.
that's the cycle.
That's the whole cycle, all right?
4 goes to 6.
6 goes to 8. And then that's the end of the cycle.
And then you just
And
have
9 just goes to 9.
All right, picking up on that pretty quick. Okay. Now, we want to know how do I figure out the inverse of these permutations, right? And that's kind of tricky. So first, let's just do it manually, and then we'll write it out and see if we can notice any patterns. Okay, so for the inverse function, what does 1 go to?
7.
7. Is anyone confused how we got that 7?
Oh, no.
Make sense?
Yeah.
Make sure this makes sense. Okay, it's just right there. It's like we're reading it back. We're flipping these rows places. That's what we're doing. Okay, so 1 goes to 7.
2
2.
goes to 1.
1.
5, 5,
5.
8,
8.
3, 4, 2, 6.
This is reading at me so much. How are you doing that so fast? Do that fast.
No, that's not right.
That is right.
It is right.
Is it?
Yeah.
I'm pretty sure.
I was just trusting you guys, so I had to check it. I just went on the assumption they're wrong. Okay, so now let's write that in cyclic notation. Right? What does 1 go to?
7.
And 7 goes to?
2.
And 2 goes to?
1.
So we're done.
Yeah.
Next cycle.
3
3.
goes to 5. And
Isn't it 5, 3?
It is 5.
3 goes to 5. And 5 goes to 3.
Wait,
And we're done.
Yeah.
Oh, yeah.
No, 4.
Okay.
What'd you say?
4 goes to 8.
8. And then 6.
And the last one's 9.
Okay, so here is how we would write it in cyclic notation reversed, or not reversed, the inverse of pi in cyclic notation. Now look how it was in cyclic notation, and look at its inverse. Do you see a pattern?
Yes.
Yeah.
But what does it do if the parentheses has 4 objects in it? Numbers?
If it has 4?
Like the ones that we did, just because of our example, the parentheses only had 3 numbers in them.
That just meant our cycles only had 3 terms. Up here we had 4. Because this 2 cycles, one had 4, one didn't.
Yeah,
Oh, you're saying what's the pattern? Here's the pattern in general. So here's another way of writing the same thing. And now I'm just going to do it based off of how I know, what I know from just doing it. So 7, 2, 1, 5, 3, 8, 6, 4, 9. So this is the same thing as this. Let's check. This says 1 goes to 7, goes to 2, goes to 1. This says 1 goes to 7, goes to 2, goes to 1. Yep, that's the same. Let's check this. This says 3 goes to 5, goes to 3. This says 3 goes to 5, goes to 3.
So we can write the inverse like that?
Yeah, so the way that you get the inverse of a function is you just flip the order around of each of the cycles.
Then why was that different?
We just wrote them different, but they're the exact same function. What does this say? This says 4 goes to 8, goes to 6, goes to 4, goes to 8, goes to 6, goes to 4, goes to 8, goes to 6, blah, blah, blah. This says 4 goes to 8, goes to 6, goes to 4, goes to 8, goes to 6. They're the exact same thing.
Okay.
So that's what I meant by there's more than one way to write these out. So the trick is, all you need to do is write them in inverse order, and then you can shift your cycles as much as you want to make it start with the number you want, right?
But we don't have to like...
So notice that if I shift my cycle over 1, that puts the 1 back over here, and we got the same thing up there. if I shift my cycle 1, that pushes a 3 off and back around here. If I push this cycle once, that pushes a 4 around to there, and then that's already the same. So they're the exact same thing, but rather than having to think about how do I get my inverse and go through all the this way, there's the easy way to get the inverse. So this is the kind of stuff that your homework problem's going to be. It's going to be like find the inverse of this permutation or something like that. Okay. Done with that. Okay, now, before we do that, let's have a brief conversation. First off, what's the simplest permutation? If I'm looking at the set 1, 2, 3, 4, 5, what's the simplest permutation on that?
Wouldn't it be like the identity?
Just the identity. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5. What would be like the second simplest permutation? So, so here's what we're saying is the simplest. Now, obviously simplest isn't a defined term. We're just using intuition for what we mean. So we're saying this is the simplest permutation on that set, right? The question is, what's the next simplest one that you can think of?
The identity function. Well,
It'd be
Well,
like
not
one
the
goes
inverse.
to 2 goes, well,
the inverse of it, like 1 goes to 5, 2, like
backwards.
switch around all the second elements maybe.
1, 5, 2, 4, 3, 3.
What about if we just swap 2 elements? So instead of that, we just, 1 goes to 2, 2 goes to 1, and then we left the rest the same.
I guess so.
Now, obviously, it's debatable whether or not this is the next simplest, but this is what I was hoping you'd say. So this, when we take a permutation and we only swap 2 elements, is called a transposition. It's a permutation where all we do is swap 2 elements, and that's it.
From the identity.
From the identity. You start with the identity, swap 2 elements, and then leave it alone. That is what we mean by transposition. Now I'm going to give you the definition of transposition. It's going to be kind of dense, but this is exactly what it's saying. Okay, so a permutation tau, from here on out I'll typically try to reserve tau for transpositions, since transposition starts with a T, right? Make sense?
Sure.
Okay, so a permutation tau in Sn is a transposition provided that 2 things. 1, there are 2 numbers in there that aren't the same number, such that tau of the first number is equal to the second number, and tau of the second number is equal to the first number. In our case, those were 1 and 2. So notice, tau of 1 is 2, and tau of 2 is 1, if we call this tau. So, first, there has to be 2 things in there that aren't the same, such that they're paired with each other, is one way to say that. And for any other elements in there that aren't those 2 elements, they just map to themselves.
Yeah.
So that's the same way as saying we just swap 2 elements. That's what transposition is. Does that make sense to everyone?
Is that
Yeah.
second number that you have listed a J?
I, J. Yes.
Okay.
J. It's because I write those iotas and my hand gets used to curving that way. Okay. So yeah, there exists I and J in that set with I not equal to J such that I maps to J and J maps to I. And for any other element K that's not I and not J, K just maps to itself. Make sense?
Mm-hmm.
That's a transposition. So let's represent a transposition now in cyclic notation. So here's a transposition. 1 goes to 1, 2 goes to 4, 3 goes to 3, 4 goes to 2, 5 goes to 5. So I swapped 2 and 4, right? And that's all I did.
Yeah.
When we represent this in cyclic notation, 1 just goes to 1, right? 2 goes to 4 goes to 2. Then 3 just goes to 3, 5 just goes to 5, right? And imagine that I did this all the way to 100. Imagine that we were talking about some massive permutation. Then I'd also have 6 goes to 6, 7 goes to 7, 8 goes to 8, 9 goes to 9, 10 goes to 10, blah, 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 continuing, right? It can be very obnoxious, very annoying. We don't want to write all that. all we really care about is this piece of it. Everything else is obvious. So that's how we represent a transposition. So when you see 2, 4 in parentheses like this, we're not talking about a point, we're not talking about an open interval. We are now talking about, in this context, a permutation. What is this? This is a bijection on the set 1, 2, 3, 4, 5 to the set 1, 2, 3, 4, 5. That maps 1 to 1, 3 to 3, 4 to 4, 5 to 5, and 2 to 4, and 4 to 2. So now we have this notation for representing some big function. Good?
Okay.
All right. And notice it only makes sense to talk about this if we know what S sub n is. So we're assuming in this case it was in S sub 5. Right?
Yeah.
Okay. So let's see what I'm doing here. Oh. So why do we like transpositions? Or what are transpositions useful for? It turns out every function we can represent as a composition of transpositions. So we can break up some complex permutation up into just a bunch of little transpositions. And then we just compose all the transpositions together, and that's our whole function. Does that make sense what I'm saying?
A little bit.
Yeah.
A little bit? Okay, let's just do the example and then maybe we'll see it. So let's look at this permutation. What does this permutation do? This is in cyclic notation. It maps 1 to what?
2,
2 to what?
3,
3 to what? 4 to what?
4,
5 to what? Okay. So you understand what this permutation is?
Yeah.
Okay, now we're going to represent it as a composition of transpositions. This is another thing you're going to have to do on your homework a lot. So make sure you understand it. First, I'm just going to give you answers, and then we're just going to go through it mentally to see that it works. So I'm saying this cycle, this permutation, can be represented as this function composed with this function, composed with this function, composed with this function.
Okay. How?
yeah, how?
So to help get your intuition for it, rather than just staring at it to get it, we're going to manually compute what this is and see that it's the same as this, and hopefully that will help.
Okay.
Okay? So let's start with 1. So what does this function map 1 to?
2.
2,
2. What does this map 2 to?
2.
2. What does this map 2 to?
2.
2. What does this map 2 to?
Wait, what?
2.
Remember when you do function composition, you apply this function, then this function, then this function, then this function, and what comes out when you're all said and done is what function composition gives you, right?
Yeah.
You remember that?
Yeah.
So Leah remembers.
I do.
So, this function maps 1 to 2. Right? So once this function operates on 1, we have a 2. So now we plug a 2 into here, and what do we get?
2.
How?
What is this function?
1, 2, 3.
This is a function, 1 goes to 3, 2 goes to 2, 3 goes to 1, 4 goes to 4, 5 goes to 5. It's a transposition. It maps everything to itself, except it maps 1 to 3 and 3 to 1.
Okay.
Make sense?
Yes.
So let's restart. We're plugging 1 in. When I plug 1 into this function, what do I get?
2.
2. So now I have a 2. When I plug 2 into this function, what do I get?
2.
2. When I plug 2 into this function, what do I get?
2.
2. When I plug 2 into this function, what do I get?
2.
2. So when it was all said and done, 1 went to 2. Okay, now let's plug 2 into it and see what we get. When I plug 2 into this, what do I get?
1,
When I plug 1 into this, what do I get?
3,
When I plug 3 into this, what do I get?
3.
When I plug 3 into this, what do I get?
3.
So when I plug 2 into the whole thing, I got 3 out. Right?
Yeah.
Alright, let's plug 3 in. When I plug 3 into this, what do I get?
3.
3.
When I plug 3 into this, what do I get?
1.
When I plug 1 into this, what do I get?
4.
When I plug 4 into this, what do I get?
4.
So 3 goes to 4.
Oh, it was the very last. Okay, wait. Did you change it? Okay, wait.
I
Do
didn't
it one more
change
time.
anything.
Do it one more time.
Alright, let's plug 4 in.
Okay.
When I plug 4 into this, what do I get?
4.
4.
So I still have a 4. So then
Okay.
plug 4 into this.
You're 4.
4.
I still have a 4, so plug 4 into this.
One.
I now have a 1. Plug 1 into this,
Get a 5.
so a 5 comes out.
That makes so much sense.
And then finally plug in the 5. Plug 5 into this, what do I get?
5.
So a 5 comes out, and a 5 goes into this, what do I get?
5.
So 5 comes out, 5 goes into this, what do I get?
5.
5 comes out, 5 goes into this, what do I get?
1.
1.
Holy suck.
So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. Exactly what this says. That's how the author gives it to you. I hate that way of thinking about it. This is the way I like to think about it.
Thanks for
Okay,
struggling us through that and then saying.
Well, if the author likes to think about that way, then maybe it's better for people in general. Why is my opinion better than the author's? Just playing the odds is probably worse, right? Okay, so now let's look at this function. Here's the way I like to think about it. When we plug 1 into this, what do we get?
1,
1. When we plug into this, what do we get?
1, 1, 2.
So 1 goes to 2. When we plug 2 into this, what do we get?
2, 3, 3.
Plug 3 into this, what do we get?
3,
4.
4, 4, 4.
Plug 4 into this, what do we get?
5, 5, 5.
And when we plug 5 into this, what do we get?
4, 3, 2, 1.
1. So, okay, wait.
How'd you figure those out though?
Yeah.
So the pattern is, when we look at this, you do this composed with this, composed with this, composed with this. That's what the author is doing. The way I did it is you do this composed with this, or this composed with this, composed with this, composed with this.
So, like, what would our homework be asking us to do?
Represent a function, take some function and represent it as a bunch of transpositions,
And
or they'll give you a function and you're supposed to apply transpositions. Now the way that you can think about transpositions is as swaps. So let me show you, hopefully we don't need to reference this anymore. I'll erase this one. Let me show you how I think about transpositions happening. So I start out with, let's see, in ours we only have, what one would I just show? Oh, up here. So we only have the numbers 1 through 5, right? 1, 2, 3, 4, 5. So if you start out with the identity function, then here's what all your outputs look like, right? Then I think about this swaps 4 and 5. So after we apply that transposition, we now have this. This swaps 3 and 4.
it's 4.
Did I?
4 and 3.
2, 3.
There's supposed to be a comma there. So that swap that, 3 and 4. This swap 2 and 3. And then this swap 1 and 2. So now 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. Remember, we were just messing with the outputs, right? The top row is still always 1, 2, 3, 4, 5. We were only messing with the bottom row. So you start out with the bottom row, 1, 2, 3, 4, 5, and then this is just telling you swap these two elements, then swap these two, then swap these two, then swap these two. And doing those swaps, we got this, which is exactly what we wanted. If we would have done these swaps instead, it still would have worked. So that's one way you can think about it, is applying swaps.
That's what it means to apply a transposition to a function.
Yep. Swap.
So it's just going to ask us.
I don't know about what it means. It's a very useful way to think about it.
So it's just going to ask us to apply the swap?
I think. I don't remember. I haven't done these problems in forever. We'll see what I give you. I remember I tried to take it easy on you. Maybe I downplayed it and told you it's going to be easier than it's actually going to be. So hope you've been paying attention. Because the video stopped recording as well. So it's not online.
Did it for real?
Guess we'll see. Okay. Next. So now let's do a more complicated one, just using our tricks rather than having to think through it all. So let's look at pi is equal to this permutation, kind of a big ugly one, right? And now we want to represent that as a composition of transpositions. Well, I can represent this as this.
Yeah.
Just using, now I'm using my trick, not the author's. I don't like the author's way of thinking about it. Because the way I actually think about this in my head is I just do 1, 2, 2, 3, 3, 4, 4, 5. So I don't even try and think about it backwards. I just think about it left to right. And then 6, 7, 7, 8, 9. Why don't we have a 9 in here?
Because there's no swap.
Yeah, we're never swapping with 9. We leave 9 completely alone. Good. Means you guys are keeping up. So this is how we could represent that with transpositions. There's tons of ways we could represent this with transpositions. This is just one way. There isn't one answer to the question. Make sense?
Mm-hmm.
Question. How many transpositions could I use to represent pi? Is it infinite?
No.
It is infinite. Should I tell you why?
Yeah.
Because I could go back and forth, swapping from here on out 1 with 2, and then 2 with 1. And I could do that over and over again, just swapping them back and forth, back and forth, back and forth, do it an even number of times. I'm back where I started. Does that make sense?
No.
No.
So, imagine, so I've got this function that I want, well, let's just take a really, really simple one that's already just basically transposition. So let's look at 1, 2, 3, 4, 5, and I'm trying to represent the function 1 goes 1, 2 goes 2, 3 goes 3, 4 goes to 5, 5 goes to 4. I'm told represent this with transpositions. Now this is just a transposition. We swap 4 with 5, right?
Yeah.
Yeah.
But it's also a transposition. We swap 4 with 5, swap 4 with 5, swap 4 with 5. Right? We swapped 4 and 5, then we swapped them back, then we swapped them again.
Oh, no, I didn't. Okay.
Right?
Oh my word. Yeah.
So I can keep adding an even number of swaps afterwards, and it doesn't change my transposition, right? So there's an infinite number of transpositions we can use to represent any function, or any bijection, or any permutation. Make sense?
Yeah.
Okay. Alright, so we call a permutation even, provided it can be expressed as an even number of transpositions, otherwise we call it odd. So is this function even or odd?
Even.
It's odd.
One of you is better at counting than the other.
I don't get it.
Which function did you point to?
This one. Is this function even or odd? It's
Oh.
odd. How do you know it's odd? Here we have it represented as transpositions. How many are there?
7.
7.
7 is odd.
You're saying the whole entire thing?
The permutation pi
I thought you were
is
saying
odd.
10, 11.
Oh, no, sorry. Yeah, the whole thing.
Okay.
So we represented it as an odd number of transpositions. So that's what we're saying here. We call permutation even, provided it can be expressed as an even number of transpositions. Otherwise, it is said, or otherwise it is odd. We're going to prove later, if you can represent a function with an even number of transpositions, then you can't represent it with an odd number. So even though there's an infinite number of ways I can represent transposition, all those representations are either going to be even, or they're all going to be odd. I can't find an even and odd number of transpositions that both represent the same permutation. Does that make sense?
Yeah.
So we're going to prove that, but
So, is it because of 9 that it's odd though? Because 9 is always going to be with itself and it's not going to be the other way?
no, it has nothing to do with that. There's no way that you could just stare at this and say, oh, it's going to be odd because,
Oh, okay.
like, not a chance. So we're going to work up a lot to help you understand why it is that case. Ultimately, proving that that is the case is what we're basically focusing on from here on out.
Really?
Yeah. Okay. So the sign of a permutation. We say that the sign of a permutation is +1 if it's even, and -1 if it's odd. So we're going to make up this little sign function. The sign function, you give it a permutation, it spits out +1 if pi is even, and it splits out -1 if pi is odd. So rather than calling it even or odd, we want to represent it with +1 or -1. And you'll see why we want to do that in a second. But note now, if pi is equal to the composition of n transpositions, then the sign of pi is equal to -1 to the n. Note that if n is even, what's -1 to the n? If n is even, what is -1 to the n?
Positive.
+1. +1. If n is odd, what's -1 to the n?
Negative one.
-1. You getting lost?
Yep.
Were you good up here?
Yep.
Okay, so now we're here.
Yep.
So this is a function. You give it a permutation, and it's either going to spit out 1 or -1. That's all it does.
Okay.
If the permutation is even, it spits out +1. If the permutation is odd, it spits out -1. What does it mean for a permutation to be even?
It has a +1.
Well, I want you to understand so that we can understand the function.
It has an even amount of the.
Transpositions. And it's odd if it has an odd amount, right? So what are we saying? So I'm saying if pi is n transpositions, well then if n is even, what's the sign of pi?
+1.
And if n is odd, what's the sign of pi? And -1 to an even number is? What's -1 squared?
1.
What's -1 to the 4?
4. -4.
Okay,
I don't know.
we're in trouble.
Oh, is it just -1?
-1 to the 6, or to the 4, is equal to -1 times -1 times -1 times -1, right? But what's -1 times -1?
1.
What's -1 times -1?
1.
So it's 1.
Yeah.
Okay, so now what's -1 to the 50?
It's probably 1.
Probably. It's also probably -1. If I have 50 -1s, then that's going to give me, how many pairs of -1s do I have?
25.
So I have 25 ones. What's 1 times 1 times 1 times 1 is 25 times?
1.
1. So anytime we put an even number up here, it's going to come out 1. Anytime we put an odd number out there, it's going to come out -1.
Oh, okay.
Okay?
Yes.
So now does this make sense?
Mhm.
So notice, sine of pi, here's one way that you can get it. -1 to the n, where n is the number of transpositions. We good to continue now?
Yes.
Now that we figured out how to calculate -1 to the 4? Okay, now I need to move the camera. Hopefully we can just go without battery for the rest. Okay, that works. Okay. So, what are we doing now? Okay, if we have two permutations, pi and sigma, then the sign of pi composed with sigma is the same thing as the sign of pi times the sign of sigma. That's what we're going to prove. Alright, so let pi and sigma in Sn and assume that pi can be represented as A transpositions and sigma can be represented as B transpositions. We don't know anything about A and B, it's just a number of transpositions that make them up, right? Then, the sign of pi composed with sigma is equal to -1 to the A plus B,
Yeah.
which is equal to -1 to the A times -1 to the B, which is the sine of A times the sine of B. Anything weird there? Why is this equal to this? Because the function here is A transpositions composed with B transpositions, so we have a total of A plus B transpositions. Right?
Yeah.
Yeah. Okay. Any questions there? You just hoping that's not going to come up on the homework, and we'll just try and keep going?
Yeah.
Okay. Then we better keep going. Okay. If pi and tau are permutations where tau is a transposition, then pi composed with tau has one more or less cycles than pi has. So when I take pi, however many cycles it has, when I compose it with the transposition, I either got rid of a cycle or added a cycle. We're not going to rigorously prove this, we're just going to try and make it very clear to your intuition. So, imagine I have pi is this, and it's obviously composed of 2 cycles. Right?
Yes.
So, if I take pi and I transpose it with something where the elements are from 2 different cycles, then we're going to end up with sigma, and it's going to combine the cycles. And now when I take sigma, and I compose it with a transposition where both the elements are from the same cycle, it splits it into 2 separate cycles.
Okay.
So, if this is a piece of my function, 2 cycles, that my transposition has an element in each of them, it's going to connect the cycles. And if both my elements in my transposition come from the same cycle, it's going to split the cycles. And so I'm either going to add a cycle or remove a cycle when I compose with the transposition. When I took this and composed it with the transposition, I added a cycle. When I took this and composed it with the transposition, I got rid of the cycle. Does that make sense?
Yeah.
Okay. Yeah.
And one way to think about it, I don't know if that works. Well, I don't want to say anything that's not true, that would just be confusing. Is there anything weird about that? Anything confusing? Anything you want to talk about more?
Well, I don't know how you're using 4 and 7 to do that.
Oh, composing 4 and 7 with this? So, let's just see what everything goes to. What does 1 go to when I run it through this? 1, and then I run it through pi. Pi is this. 2. So 1 still just goes to 2.
Okay.
And 2 still just goes to 3. Right? And 3 still just goes to 4. Because this one doesn't change what 3 goes to, so 3 just still goes to 4. So only when we get to 4 that we get something different. So now 4, instead of 4 goes to 5, we got 4 goes to 7 goes to 8. So now 4 goes to whatever 7 used to go to. 7 used to go to 8, now 4 goes to whatever 7 used to go to. And 7 is going to go to whatever 4 used to go to.
Oh. So you can pick any numbers from both of them?
Yeah, it's just a way of combining the cycles. When I did this, what did I do? I made 4 go to whatever 7 used to go to, and I got rid of this. And I made, so 7 no longer goes to that, but 4 goes to that. And I made 7 go to whatever 4 used to go to, like that. And that's what this is.
Okay.
Make sense?
Yeah.
And then when we split it, so now I've got this picture, and now I'm going to split it. What am I going to do? I'm going to make 4 go to whatever 7 used to go to. So now 4, instead of going to 8, it goes to whatever 7 goes to. 7 goes to 5, so now 4 goes to 5. And 7 goes to whatever 4 used to go to. 4 used to go to 8, so now 7 goes to 8. And it split the cycles. Make sense? Okay. Alright. So next, given some permutation, pi in Sn, we're now going to use C of pi to represent the number of cycles in pi. So if this were pi, pi is 2. If this were pi, pi is 1. Or sorry. If this were pi, C of pi is 2. If this were pi, C of pi is 1. Is the number of cycles in a permutation. Right? What about when we come back and look at this one? What's C of this? 4. There's 4 cycles. 1, 2, 3, 4. 4 cycles. So C of pi is just the number of cycles in pi. That's what we're going to define it to be. Now notice that C of pi composed with a transposition is going to be C of pi plus or minus 1. If we compose with the transposition, we either added a cycle or we removed a cycle. Right?
Okay.
Yeah.
Okay. So now, we're going to do a proof. We're going to prove that if pi is equal to A transpositions, and pi is also equal to B different transpositions, where each of these are transpositions, then A and B have the same parity. Either they're both even or they're both odd. We're going to prove that. Did you understand what I just really said here?
Those two pies are the same.
Yeah, same pi. If I can represent pi as A transpositions, call them tau 1, tau 2, tau 3, tau 4, all the way up to tau A, and I can represent pi as B transpositions, sigma 1, sigma 2, sigma 3, sigma 4, all the way up to sigma B, then A and B have the same parity. They're either both even or they're both odd.
Because they're both transposing the same
How do you know?
permutation.
They're both decompositions of the same permutation. We don't know. We're going to prove.
Oh. Okay.
So yes, how do we know? Wonderful question. Let's see how we know. But do you understand what we're trying to prove?
Yes.
Yeah.
Okay. Now I'm going to write this, and this is saying the exact same thing. Let's connect the two. If pi is a permutation, where pi can be represented as A transpositions, then A is congruent to n. What's n? It's the same n as that S of n. It's the number of elements in our set. A is modulo congruent to n minus the number of cycles mod 2.
I'm so confused.
Mod 2 gives us a 1 or a 0, right?
Yeah.
It gives us a 1 if the number's odd. It gives us a 2 if the number's even. Or it gives us a 0 if the number's even, right?
What?
Sorry. I'm thinking mod 2, not congruent mod 2. Sorry. When you do congruence mod 2, this is only true if both numbers are even or both numbers are odd, right?
Yes.
Okay, that's what I meant to say. So, notice that this is a constant, whatever it is. N minus the number of cycles in pi, that's a constant. Right?
Yeah.
So A has the same parity as a constant, no matter what A is.
Okay.
So for any A, for any number of transpositions you can use to represent pi, it has to have the same parity as this number, this constant. So if this constant is odd, A is always going to be odd. If this constant is even, A is always going to be even. So in other words, if we prove this, then we've proven this.
Okay.
Why?
Okay, let's say this again. Here we're saying, if I can represent pi with two different series of transpositions, if I can represent pi with A transpositions and I can represent pi with B transpositions, then A and B have to have the same parity.
Yes.
This is saying, no matter how you represent pi, no matter how many permutations you use to represent pi, I'm using A here, but this A has nothing to do with that A. New story, new chapter. If I can represent pi with any number of transpositions, call it A, whatever that number is, it has the same parity as this constant.
What does that constant have to do with anything?
This constant, once I know what pi is, this is a constant. Let's look over here. What is this number when we're looking at this? What's n when we're looking at this permutation?
2.
9. What?
There's
Oh, 9.
Yeah. Is that what you're getting lost on, what the n is?
Yes.
Okay.
I'm getting lost in that whole
The
thing.
n is the same as this s sub n. It's the number of elements in our permutations.
Okay.
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 C of pi is the number of cycles in pi. How many cycles are in here?
2.
2. So, 9 minus 2 is
7.
7. So, when we're talking about this permutation, any series of transpositions I can use to represent this permutation has to have an odd number of transpositions. Because the number of transpositions we use to represent it has to be congruent, has to be congruent mod 2 to this number, which is a constant. This number is always 7
Oh.
for this particular pi.
Okay.
For this sigma, our number would be 8. Right?
Yes.
And so any number, any decomposition of this function into a composition of transpositions, is that a lot of big words? Any way I can represent this function as a composition of transpositions is going to use an even number of transpositions. That's what this is saying.
Okay.
So it's saying once you pick your permutation, this number is a constant. It's set in stone. You can't change this number. Right?
Yeah.
So no matter what series of transpositions you use to represent it, this number is still always this number. So, all those transpositions have to have the same parity as this number.
Yes.
If this number is even, A has to be even. If this number is odd, A has to be odd. So notice what this is saying now. This is saying if I can represent pi with 2 different series of transpositions, they have to have the same parity. Yeah, they do, because they have to have the same parity as this constant.
Yeah.
So proving
because
this
that
and proving
constant-
this are the same thing.
That constant is going to be. all
That constant is a
transpositions.
constant, it's just a number. Once I pick my pi, that number is already set in stone. So this A has to have the same parity as that number, and this B has to have the same parity as that number. Therefore, they have to have the same parity as each other. Does that make sense?
Yeah.
Okay, yeah. All that yelling is standard. Turn. Okay. Let's prove it. So, let pi be some permutation represented by A transpositions. Good so far?
Yes.
Now consider this table. We're going to start out with iota, the identity function, and then we're going to compose the first transposition with it, T1. She needs that. She needs that. And I don't have calculus homework, so that should be it. Yep, thanks. Okay. Where was that? Consider this. Okay, so we're starting out with the identity function, right? And then we're doing the identity function composed with the first transposition. What is the identity function composed with the first transposition? Just the first transposition.
Yeah.
Yeah.
Now, we're going to look at the first transposition composed with the second transposition. And then the first transposition composed with the second, composed with the third. And then the first composed with the second, composed with the third, composed with the fourth, etc., all the way up to the first composed with the second, composed with the third, all the way down to composed with the eighth. With me?
Yes.
Yeah.
And we're going to make this a cute little table. So, on the left-hand side, we're showing the function up to that point. So first we've got just this, then we compose tau 1 with it, then we compose tau 2 with that, then we compose tau 3 with that, then 4 and 5, all the way up to composing tau A with it, right? Now notice, what is this constant for the identity function? How many cycles are there in the identity function?
And 0.
don't think anyone said the right answer, but I'm not positive. There were such wild answers. How many cycles are there in the identity function?
Oh, there's one.
There's 0. There's n.
There's n!
Oh.
You have 1 goes to 1, that's a cycle. You have 2 goes to 2, that's a cycle. You have 3 goes to 3, that's a cycle. All the way up to n goes to n, right? Is there anyone confused by the fact that the identity function has n cycles?
No.
Everything just maps to itself. It makes its own cycle. This counts as a cycle. Maybe you don't want this counted as a cycle, but this is a perfectly valid cycle. Let's say we throw on here, and 10. What does that mean? That means 10's up here and it's all by itself and it goes to itself. It's its own little cycle. Right? Okay. So, the identity function, when you do n minus the number of cycles it has, you get a big old 0, because it has n cycles. Right?
Yeah.
Now you compose a transposition with it. You either added a cycle or removed a cycle. Now you can't you can't add a cycle when there's already n of them. All you can do is remove a cycle, right?
Yeah.
I've got the identity function. If they're all just their own little cycles, and I've got to combine, and I apply a transposition, I'm going to hook 2 of those little cycles together to create a cycle of 2 now, right? So we made the number of cycles 1 smaller, or in other words, n minus the number of cycles is now 1. You good?
Yeah.
What? N minus the number of cycles.
Yeah, that's what this is. N minus the number of cycles in sigma. When this is what sigma is. When sigma is the identity function, the number of cycles in sigma is n minus n is 0. Now we're applying a transposition.
Yeah.
Here's another way to think about it. How many cycles are there in a transposition?
N.
There's not n.
How many cycles? N minus 1.
N minus 1, right? We start with n cycles when we have the identity function, and now we need to connect 2 of those cycles together. So we got rid of a cycle. We took 2 cycles and we merged them together into 1 to make a bigger cycle. So we have n minus 1 cycles. So n minus 1 is 1.
What would it be? Minus 1?
No.
Don't worry. No, wrote it the negative.
n minus 1. If I take a number and I minus a smaller number, I better end up with a positive. Sanity check. But that's also equal to n negative 1 plus 1. Oops, I said n, but I wrote 1. Which is equal to 1. Let's see an example. What is 8 minus 7 equal?
Oh, it was 6. I mean, no, actually.
7, right? No, it's 1.
It's 1, yes. Sorry.
Alright. Okay. Ready to continue. So are we okay with the fact that now a transposition has 1 cycle?
Okay.
Yes. No. Is anyone not good with that? You're not good with it? Oh, you are good with it. Okay. Now, when we apply a transposition to that transposition, we either added a cycle or removed a cycle. We don't know. We could have undone the cycle that we just added, or we could have added a different cycle, right? And from there on out, every transposition that we put on it, it's going to give us a plus or minus 1, plus or minus 1, plus or minus 1, plus or minus 1, right? And how many of these ones are there? There's A of them, because we apply A transpositions. 1 give us when 1. 1, 1. When we did 2 transpositions, we have 2 ones. When we have A transpositions, we're going to have 1, plus or minus 1, plus or minus 1, plus or minus 1 for a total of A terms. Okay? Now, observe that if I'm missing words. Observe that this is even. Is even, should be right there. So observe that 1 plus or minus 1 plus or minus 1 plus or minus 1 blah 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 is even if there is an even number of ones and odd otherwise. In other words, if we do 1 plus or minus 1 plus or minus 1 plus or minus 1, and I do this an even number of times, I'm guaranteed to have an even number. I don't know what it is, but it's even. And if I do it an odd number of times, I'm guaranteed to have an odd number. Right?
Hold on.
Is 1 even or odd?
So,
Odd. So right here we're odd. If I plus 1 to 1, what do I get?
you got another. I mean,
You get 2,
yeah.
which is even. If I subtract 1 from 1, what do I get?
Even.
0, which is even. So then I got an even. Anytime I go 1 away from an odd, I've got even. Anytime I go 1 away from an even, I've got an odd. So I'm odd, then I'm even, then I'm odd, then I'm even, then I'm odd, then I'm even, then I'm odd, etc. So if I have an even number, then it's going to be even. If I have an odd number, then it's odd.
Okay.
Okay. So, all these things, the sum of all these things is even if there's an even number of ones and it's odd otherwise. Therefore, n minus the number of cycles has the same parity as a.
Okay.
Because this is this, which is even if a is even and odd if a is odd. So this sum has the same parity as a, or in other words, this has the same parity as a. And now we proved it. And then we have a small little corollary up there. If pi is a permutation, then the sine of pi is equal to -1 to whatever that constant is. Right? Because if that constant's even, then the sign has to be 1. If that constant's odd, then that sign has to be -1.
Yeah. It's the same thing like that.
Yeah.
And that's it. Permutations.
That was so difficult.
Huh?
That was a lot.
I know. Permutations are dense until you get comfortable with composition, then they're actually real easy. Like I said before, trying to understand these, even just understanding this, seems kind of hard for you. Yet in logic, we're not even doing math. We came across logically equivalent things and we proved things about it left and right, and you had no problem with it. So it's just because you're not comfortable thinking about composition and functions that way. Which is the whole reason that we're covering this chapter, is to try and get you comfortable with composition. Not this chapter, this section. The reason we cover this chapter is because you need to know what a function is. Alright?